When I started learning chemistry, I learned about this powerful rule called the octet rule, which says that any element, if it gets 8 electrons in its outermost shell, the valency shell, it tends to be super stable. That's why noble gases are all stable, because all of them have 8 electrons in the outermost shell. And the elements that don't have 8 electrons, well, they tend to somehow get it. For example, if elements have 1 extra electron, they tend to lose it. If elements have less than 8 electrons, they tend to gain an electron, all because they want to form 8 electrons in its outermost shell. And this becomes the core motivation for elements to form bonds. And then we go about learning different kinds of bonds and so on and so forth. But for me, the big question remained, why octet? Where does the 8 number come from? Why is it that if elements have 8 electrons in the outermost shell, they become stable? What is it about that number? I never got an intuitive answer for this question until now. So the goal of this video is, like always, pretend we don't know anything about octet or noble gases or nothing like that, and then logically, step by step, try and rediscover everything from first principles. And if I do it right, spoilers, we will see that that number 8 is not some random number, but it's connected deeply to the fundamental structure of the electron and the universe itself. So if you're ready for this, let's begin. So Feynman, how do we logically predict which elements are noble and which elements are reactive? Feynman says, Mahesh, chemistry at the heart of it is all about transfer of electrons. So there are two things that we can think about. First, if you take any element, how easy it is to pluck an electron from its outermost shell. In other words, how much energy is required to pull out an electron. We call this the ionization energy. Now, if an element has low ionization energy, that means it's very easy to pluck that electron, which means it's very easy to transfer electrons. So that element is going to be reactive. So that's one thing we can look for. But there's another thing. Just like when you drop a ball towards the earth, the potential energy reduces and gets released as kinetic energy. Similarly, if I throw an electron towards a neutral atom, then as it falls down, because of the nuclear pull, the potential energy reduces, and that gets converted into kinetic energy, which can be converted into heat and so many other things. So energy will be released. This energy is what we call electron affinity. Now, if an element has very high electron affinity, that means a lot of energy is released when it grabs on an electron, and that energy can be used to do more interesting things, like maybe pluck an electron from some other atom. Which means if an element has a high electron affinity, even then it tends to be reactive because a lot of energy gets available. So look, this means if an element has low ionization energy or high electron affinity, it tends to be reactive. Now, in contrast, Mahesh, what if an element has high ionization energy and no affinity at all to electrons? Then it's very hard to pluck an electron, and it will not even try to grab an electron because no energy will be released. Then this element will be non-reactive. In other words, the element will be noble. That's how we can logically figure out which elements are noble. And that sounds pretty interesting for me. All right, so that makes sense. But now the big question is, how do we logically figure out the ionization energies and the electron affinities of different atoms? And Feynman says for that, we need to now have a model of an atom. Well, the most intuitive model is the planetary model, but it does not have a lot of predictive power. In contrast, the most accurate model is the quantum mechanical model. Here, for example, we do not think of electron as orbiting the proton in hydrogen, for example. Instead, we like to think that the electron is forming some kind of a standing probability wave. You can kind of think about that in 3 dimensions. Very hard to imagine that. However, if you try to look at it or make a measurement, that whole wave collapses to a particular point, and now you measure an electron at a specific point. Stop looking at it, and again, it evolves to form a stationary wave. Look at it again, it collapses to a particular point. That collapse is random, okay? But if you do it enough number of times, you will now see a map being formed, a probability map of, where is the high chances of finding an electron. This is what we call an orbital. And this is the way quantum mechanics deals with the model. This is the quantum mechanical model of the atom, okay? So this is what the ground state looks like. On the other hand, if I supply some energy to it, the electron gets excited, and now it can have different probability maps. For example, in the first excited state, it might look like this, or maybe like this, and so on and so forth. And we've talked about these different kinds of orbitals, their shapes, and all about them in our previous video. But you don't have to watch that video if you haven't already, okay? What's necessary for the sake of this video is that in the first energy level, you have only one orbital. In the second energy level, you have 2 square, 1, 2, 3, 4 orbitals. In the next allowed excited state, energy level, you have 3 square 9 orbitals and so on and so forth, okay? Now, the important thing is that you can see this is just for 1 electron. This is just for the hydrogen. Imagine you have 2 electrons and more electrons. Oh my God, things are going to become super complicated super fast. So this is very complicated model. So what do we do? Well, the best way to move forward is to sort of use a model in between. In fact, we're going to take insights from our quantum mechanical model and use it to upgrade our planetary model. I feel that's the best way to go forward, in which we ensure that there's still intuition intact and it's still pretty accurate, okay? All right, so what insights do we need from the quantum mechanical model? The insight is that each orbital has a maximum capacity of just 2 electrons. This comes from the Pauli's exclusion principle, which is probably a topic for another video, okay? As a result of that, the first energy level, since only has 1 orbital, it can accommodate a maximum of just 2 electrons. The next energy level has 4 orbitals, so it can accommodate 4 times 2, 8 electrons. The next one has 9, so 9 times 2, 18 electrons, and so on and so forth. And now let's use this to upgrade our planetary model. So we can now say in our planetary model, the first shell can accommodate 2 electrons. The next shell can accommodate 8 electrons. The shell after that can accommodate 18 electrons, and so on and so forth. All right, so now that we have an upgraded planetary model, let's see if we can use that to think about ionization energies and electron affinities. So let's start with hydrogen. It has 1 proton and 1 electron, and we'll use hydrogen as our baseline. We'll look at the numbers for hydrogen and use that to predict the ionization energies and the electron affinities of all the other elements, okay? All right, so what is the ionization energy of hydrogen? One can actually mathematically calculate this, and it turns out to be somewhere close to 14 electron volts. And experimentally, it's hard to ionize hydrogen, which means 14 electron is pretty high value of ionization energy, just to get some feeling for numbers, okay? What about its electron affinity? Well, let's just shoot an electron towards it and see whether it can grab it. Well, an electron will experience an attractive force from the proton and some repulsive force from this already present electron. But you can kind of see the attractive force is larger, so the hydrogen will be able to grab onto an electron and some energy will be released. And that energy released happens to be about 0.7 electron volt. And it turns out in nature, we do find hydrogen minus ions. For example, we do find hydrides, lithium hydride, sodium hydrides. So this means that 0.7 is pretty decent value of electron affinity. Okay, so with these numbers in mind, now let's think about all the other elements. So let's go to the next element, helium. Helium has 2 protons and 2 electrons. So what changes? Well, the 2 protons will pull on the 2 electrons much more than before, and so they will be much closer. Now, because of the electron repulsion, removing an electron becomes slightly easier, but because there are 2 protons and we are so close to it, the nuclear pull is much stronger than what we had in hydrogen. So we would expect overall the ionization energy to be much larger than hydrogen. And that's exactly what we get. The ionization energy for helium happens to be about 24 electron volts, super high. Okay, what about electron affinity? Well, for that, we need to add an electron, and guess what? The first shell is full. It cannot accommodate more than 2 electrons, so the next electron has to go into the next shell. Now, this electron experiences attraction from these 2 protons, but also experiences repulsion from these 2 electrons, and it's so far away, we can kind of model it and say that it completely cancels out. So we like to think that these 2 electrons kind of shield the nuclear pull of the protons. So the 2 electrons and the 2 protons, their attraction and repulsion cancel out, and as a result, this electron does not feel anything, which means helium will not be able to grab onto that electron at all. In other words, helium should have no electron affinity, and that's exactly what we find. It has 0 electron affinity. And look, right in front of your eyes, we have very high ionization energy, no electron affinity. That is our noble, and that's why helium is noble. Amazing, isn't it? That's how we figure things out. And before moving on, if you're wondering where I get the t-shirts, well, I make my own. You can buy them, link in the description below, okay? All right, moving on to lithium. There are 3 protons and 3 electrons. But wait a second. Feynman, in the second shell, there are s and p orbitals. Which orbital does it go into? Well, Feynman says for now, let's not worry about that. Let's just imagine that the electron just goes in the next shell. Let's not worry about orbitals, all right? Okay, just like before, because of the stronger pull, the first shell becomes even closer. And just like before, the 2 electrons over here will shield 2 protons, which means this electron effectively only experiences the pull of just 1 proton. And what we now find is, look, this is just like the hydrogen, except the electron is much farther away than what it was in the hydrogen, which means plucking it must be easier than hydrogen. So I would expect now its ionization energy to plummet. It should be much smaller than hydrogen itself, right? And indeed, that's what we find. Its ionization energy is incredibly small, so it's very easy to pluck it out, and that's what makes lithium super reactive. What about its electron affinity? I don't care about it because I already know the electron ionization energy is very low, so it's very reactive. But still, thinking about it, just like with the case of hydrogen, it can hold on to another electron. But again, we would expect its affinity to be smaller than the hydrogen because it's much farther away. And it's exactly what we find. Its affinity is slightly smaller than the hydrogen. Okay, moving on. Beryllium has 4 protons. 2 are shielded, and therefore these 2 electrons will experience the pull of 2 protons, which means increased pull, the shell comes closer. And just like before, as a result of this, look, the ionization energy, we would expect it to be higher than lithium because electrons are experiencing double the pull, twice the pull, they're closer and so on. And that's exactly what we find. It's more than what you get in lithium. And similarly, the electron affinity should also increase because there's a stronger pull. And in fact, we can now go faster. The more protons we add, as we go towards fluorine, for example, the number of protons increases, the number of electrons increases, the shell comes closer and closer. So we would expect both the ionization energy to skyrocket and also the electron affinity to skyrocket because of the higher pull, it can grab onto the electron much more easily. And if you look at the numbers, that's exactly what we find. Look, the ionization energy has increased. And similarly, electron affinity should also increase. At this point, I'm like, wait a second, Feynman, I do see some anomalies over here. And Feynman says, don't worry too much about that. If you blur your eyes, you see a trend that the affinity is increasing and the ionization energy is increasing. We'll address this a little bit later. Okay, now we add 1 more proton and go to neon. What happens? Well, again, the shell comes closer. We would expect the ionization energy to further increase very high. And what about its affinity? Well, now if I have to add another electron, the shell is full. It has to go to the next shell. And by the time it goes to the next shell, all these 10 protons are shielded by these 10 electrons. So the electron will not feel any pull. And so it will not be able to grab onto it, which means the electron affinity of neon plummets. And look, again, we have our noble. Very high ionization energy, 0 affinity. That's what makes neon noble. So Feynman says, Mahesh, let's pause and reflect for a while, okay? If you go back to lithium, why does it tend to lose electrons? Well, not because it wants to lose electron, it wants to be like helium, none of that. It's because it takes very little energy to plug that electron. It has low ionization energy, and that's why it tends to lose electrons, and that's that. On the other end of the spectrum, when you come to fluorine, why does it tend to gain electrons in chemical reactions? Well, again, not because it wants to fill its shell or it wants to be like neon. None of that. The fact is, when you grab an electron, a lot of energy is released. It has a very high electron affinity, and that's why it tends to grab electrons and become negative ions in chemical reactions. But what happens when you go to neon? Well, ionization energy increases because you have 1 extra proton. However, because you have now the next electron can only go into the next shell, the electron affinity plummets to 0, and that's why neon becomes noble. So look, what I love about this is that we are going away from wants and desires and all that loose language and concretely talking in terms of ionization energies and electron affinities. I love it. And so when you have a filled shell, very high ionization energy, 0 affinity, and that's why you get a noble. And so now Feynman asks Mahesh, when do you think will you get the next noble? And I'm like, well, the next noble element is when the next shell is completely filled. And the next shell can accommodate 18 electrons. So we would expect the next noble to be the element which has 2 plus 8, that's 10, 10 plus 18, 28 electrons. And that is nickel. Wait, what? Nickel is not noble. I know that. I know argon is noble. But that doesn't make any sense. Why is argon noble? Argon has only 18 electrons, which means in its outermost shell, it should have only 8 electrons. So why would argon be noble? Argon, I would expect to have high ionization energy, but I would expect it to also have high electron affinity because the shell can still accommodate more electrons. Why is argon noble? Shouldn't nickel be noble? What's going on, Feynman? And Feynman says, Mahesh, this can only mean one thing. It's time to upgrade our planetary model. Just like how we can upgrade our learning model using Brilliant, the sponsor of this video. If you like my channel, then you love Brilliant because just like in this channel, you get to rediscover concepts intuitively and you can actually start for free. And unlike passive videos, you can actually interact with it and actively uncover the concepts. And you can do that in various fields like math, data, programming, and even AI. And another reason I keep recommending them is because they have bite-sized lessons, which means even with 15 to 20 minutes a day, you start leveling up and become a better problem solver. Take their course on quantum mechanics, for example. Just in the first chapter, you start interacting with waves to understand superposition. You start making predictions for the single-slit experiments and rediscover ideas of wave-particle duality and so much more. And if you think that's cool, well, you can try everything Brilliant has to offer for free for a full 30 days by going to brilliant.org/FloatHeadPhysics or just scan this QR code. You'll also get a 20% off on their annual premium subscription. The link is also in the description. All right, now back to upgrading our model. So the big problem is we get the first noble gas when the first shell is completely filled. We get the second noble gas when the second shell is completely filled. However, for some weird reason, we don't get the third noble gas when the third shell is completely filled. No. We get the third noble gas when the third shell is partially filled. How does that make any sense, Feynman? And Feynman says, well, Mahesh, remember that these shells are actually orbitals? Well, let's think about them now. So if we go back to the original question that you asked, for lithium, where exactly will the third electron be in the second shell? Will it be in the 2s orbital or 2p orbital? Where do you think will it be? Let's try to answer that question. Now, between you and me, I know that the s orbital gets filled before the p orbital because we've taken some chemistry course. But remember, we're pretending we don't know anything. This is a complete rediscovery. So my answer to Feynman would be, Feynman, I don't know. They look exactly the same. They have the same energy level. So how do we figure this out? And Feynman says, well, let's look at this in a little bit more detail. Remember the whole point? We said that for the lithium, the third electron is in the outer shell, and as a result, the two electrons over here shield the two protons, and so the valence electron only feels the pull of one proton. That was the story. But is that accurate? Well, the reason why that cannot be accurate is because, remember, according to quantum mechanical model, electrons are not at a fixed distance. Remember that they are forming some kind of probability standing waves. So it's possible that sometimes when you measure this electron, it can be found inside that shield. It's completely possible. Remember, it's all about orbitals. Which means when that happens, that electron feels the full force of all the three protons. But next time when we measure the electron, maybe it materializes outside the shield. This time it will only experience the pull of one proton. Next time again, it might be, it might collapse inside, and next time again, it might collapse outside. So look, on an average, that electron is going to experience a pull of more than one proton because there is a chance that it can be found inside the shield as well. But I'm like, all right, that kind of makes sense, Feynman, but how much more? Feynman says, well, that depends upon its probability of being inside the shield. If there's a higher probability of being inside the shield, on average, it will have a higher pull. If it has a lower probability of being inside the shield, on average, it'll experience a lower pull. That makes sense, right? So now let's look at the s and p orbital and see in which case there's a higher probability of being inside the shield. So this is what the s orbital looks like, and this is what the p orbital looks like. In which case, Mahesh, there's a higher chance of finding an electron inside the shield. And I'm like, oh my God, in the p orbital, we have a node here. The probability of finding the electron somewhere close to the nucleus is 0. But in the s orbital, the 2s orbital, the node is outside. It's a radial node. So clearly, just from the diagram, you can see there's a higher probability of finding the electron inside the shield in the s orbital compared to the p orbital. Which means if we were to go back to modeling this, we could model this electron. We could say that, hey, this electron experiences a pull of, say, 1.5, protons on an average. But then what would be the pull over here? It would be less because there's a smaller chance of being inside. And so it would experience a pull of, let's say, not 1.5, just 1.2 protons as an example. So look, this means in which case it's easier to plug the electron. In this case, it's much easier, even though in both the cases, the electron is in the same shell, because here it experiences a less effective nuclear pull. It's much easier to plug the electron from here compared to here. Which means if you look at these two energy levels, the s orbital level must be deeper compared to the p orbital. P orbital level must be slightly higher, so it's easier to plug the electron from the p orbital compared to plugging it from the s orbital. That's why 2s is lower in energy compared to 2p because s orbital can penetrate the shield better compared to p orbital. Does that make sense? And I'm like, that makes sense. This is the reason why the s orbital comes lower, the 2s orbital comes lower than 2p, and that's why the 2s orbital gets filled first. It's amazing, isn't it? But now the big question is, Feynman, does this change anything about the elements that we have uncovered so far? And Feynman says, no, Mahesh, not really. Because look, the s and p orbitals are still very close to each other. So effectively, our story still holds. As we go to heavier and heavier elements, the ionization energy will keep increasing. The electron affinity still keeps increasing until the entire shell is filled, when the electron affinity plummets and we get a noble gas. But now, what happens when you go to the next element, sodium, which has 11 electrons? The 11th electron will now enter the next shell. But where? Is it in s orbital, p orbital, or d orbital? Well, again, let's look at all the three cases separately. In our naive model, we might say that, hey, all the 10 electrons will shield the 10 protons, and therefore the electron will effectively experience a pull of just one proton. But we know now that's not true, because the electron can penetrate the shield. But which orbital penetrates the shield better? Well, let's look at it. If you look at the three, what do you notice? Well, again, just like before, we see the s orbital penetrates the shield way better compared to the p orbital, and the d orbital just completely sucks. Look at that. The d orbital has absolutely no penetration at all. So in the s orbital, because of the penetration, the effective nuclear pull would be higher than one proton. It turns out to be, if you do the math, about 2.5 protons. In 3p, well, again, you can see it's lower than s, but the penetration is there. So it will turn out to be 2.2 protons, let's say. But when it comes to d orbital, look, it doesn't penetrate at all. So for d orbitals, for all practical purposes, we could say that the electron experiences a force of only one proton, effectively. And so now when you compare the three, what do you notice? Just like before, the 3s and 3p are still very close to each other, but 3d, look, it only experiences a force of one proton. It's much less tightly bound compared to these two. Plucking this electron is way easier. It takes a little bit of energy compared to these two. In other words, the 3d must be much higher compared to 3s and 3p. And so if we go back over here, the way our energy level diagram will modify is that 3s and 3p are still close to each other, but 3d, look how high it has gone. In fact, now we can quickly look at the next few elements. If you look at sodium, it's the easiest to plug that electron, so you would expect very low ionization energy. And then as we go further down, the ionization energy should keep increasing until we reach chlorine. Very high ionization energy, even very high electron affinity. But now when we go to argon, what's going to happen? We have one more proton and one more electron, so the ionization energy further increases, making it super high. But then what about affinity? Well, earlier I thought that it should have a very high affinity because there is still space in the third shell. But now you can see that if you add the next electron, the electron has to go in 3D. In fact, if you look at this carefully, 3D is even higher than 4s. And that is so weird. Even though the fourth shell is much farther away than the third shell, because the s can penetrate much better than d, the 4s orbital ends up at a lower energy than 3d. So when you add the next electron, it would effectively go to 4s before going to 3d. And if it goes to 4s, just like before, it'll be very hard to hang on to that. All the electrons below are going to shield all the protons, and that electron will not be able to hang on to it. In other words, it will have zero affinity. And that's why argon becomes noble. It's all because of the fact that 3D sucks at penetrating, making its energy level so high it's almost inaccessible. And that's why once 3s and 3p gets filled, the next electron has to go. It has no choice, but it has to go in the next shell. And that's why you get a noble gas when the 3s and 3p got filled. Now the same thing happens again. When do you expect the next noble? Well, we would expect the next noble when the 4s and 4p gets filled, because again, just like before, 4d would be much higher. So once 4s and 4p, and of course 3d would be filled by then, gets filled, we would expect the next electron to come to 5s. Very hard to hang on to it. So once 4s and 4p gets filled, again, we would expect the element to have high ionization energy, low electron affinity, zero electron affinity, giving us a noble gas. And so now Feynman says, Mahesh, let's put it all together. When do we get a noble gas? When the s and the p orbital of a particular shell gets filled. And when that gets filled, look how many electrons we end up with. We end up with 8 electrons. And that's why when you have 8 electrons in the outermost shell, you end up becoming super stable because the next electron has to go in the next shell. That explains the octet. But Feynman, what about other elements? Why do they tend to want to have octet? And Feynman says they don't. If you look at, for example, the next element, the element that comes after the noble gas over here, for example, potassium, then it's just that the next electron is in the next shell. It's so easy to pluck it, and therefore they tend to usually lose an electron. And when they do, look, they end up with 8 electrons in its outermost shell. And if you look at an element that was just before a noble gas, for example, in this case, chlorine, it has 1 less electron. And so it has a very high electron affinity. And that's why they tend to gain an electron. And when they do, look, they end up having 8 electrons in its outermost shell. It's all about ionization and electron affinities. They don't want or desire anything. So finally, answer our big question, where does the 8 electron rule comes from? Why is it that if you have 8 electrons in the valence shell, you end up with a noble gas? Well, that's because you get a noble gas when the s and p get filled. And look, since there are a total of 4 orbitals, and each orbital has a capacity of 2 electrons, 4 times 2 is 8. That's where the 8 comes from. So we could tie it back all the way to Pauli's exclusion principle. And the Pauli's exclusion principle actually comes from a deeper fact that electrons are all identical fermions. Again, fermions are elements that have half integral spins. Don't worry too much about them. But because electrons are identical and they're fermions, that's why each orbital can only accommodate 2 electrons, and therefore you get 8. Now, hypothetically, if Pauli's exclusion rule did not hold, and if an orbital could accommodate more than 2 electrons, all bets are off. 8 would no longer be the magic number. But that's not all. The second reason is because we have exactly 4 orbitals. Why do we have 4 orbitals? Well, s is spherically symmetric, so you'll always get 1 orbital. But why do we have 3 p orbitals? Well, that's because we live in 3-dimensional spatial universe. If you had more or less spatial dimensions, we would have more or less p orbitals, and again the number would be different. So it's also because of the fact that our universe is spatially in 3 dimensions. But finally, the final reason is the fact that 3D electrons, 3D orbitals and higher f orbitals, all of them suck at penetrating, and therefore their energy level is much higher, making them inaccessible. If they were accessible, then again 8 wouldn't be the magic number. But what makes them so inaccessible? Because they cannot penetrate the shields, and the shielding effect comes at the heart of it comes from the fact that electrons repel each other. And that's our reason number 3. So if you put it all together, what's mind-blowing is that the fact that electrons are identical fermions that repel each other and exist in a 3-dimensional spatial universe literally directly gives us the octet rule. That is amazing. What a connection. What a connection. Did I tell you it is deeply connected to the fundamental features of the electrons and our universe itself? Oh man. Oh man. Now, before we end the video, Feynman asks a bonus question. Remember that we thought that the electron affinities and the ionization energy should increase, but there are some exceptions. Now, with the orbital picture, now the fact that s orbitals are slightly lower than p orbitals, we can use that to explain these exceptions. And that's a homework for you. But the broader takeaway over here is I used to think that chemistry is full of rules and exceptions, and I can never make intuitive sense of them. But I was wrong. It's all about finding the right models. Using the right model, you can make things intuitive. And whenever you do find an exception, it just means that your model is limited. And once you upgrade them, the exceptions start making sense. I'll see you.